A function is a relation in which every input has exactly one output. Normally when we talk about inputs and outputs, we're talking about x's and y's. But it doesn't have to be x's and y's. If you go to a soda machine and you press a button, that's an input. The output is the soda you get out. Has anybody ever been to a soda machine where you press a button and you get the wrong thing? Yeah, somebody didn't do their job right if that happens. Oh, you got 2 for the price of 1? That's awesome. That's awesome. All right, so every time you press a button on that soda machine, you expect to get the same thing every time. That's how that's supposed to work. In functions, it's the same thing. If you put something in, you expect to get the same thing out every time. You shouldn't get 2 different things. If you went for a Dr. Pepper, you should not get a Coke one time and then a Dr. Pepper the next time. Functions are the same way. There's a few different ways we represent these. It's still up there. One of the ways we represent them is with ordered pairs. So we can write an function or a function as a relation where we have just a bunch of ordered pairs. X's and Y's paired together, parentheses around them, commas in between. All right. So 1, 2, 2, 3, 3, 2. And notice how in this example, every x has exactly one y value that it's paired with. You don't see any of the x's repeating. That's another thing that a lot of people say when they're talking about functions. X's don't repeat. If they do repeat, they should always give you the same thing for the y. All right, so that's one way. Another thing that you've seen is a table. An XY chart, some teachers call them T charts because they kind of look like a little T. And you'll see the X's or the inputs in the X column and the outputs or the Y's in the Y column. And notice how the X's don't repeat. If they did repeat, they'd always be paired with the same thing. So if I put another 1 in the X column, I'd have another 1 in the Y column. Here's another thing. This is called a mapping diagram. Back in Math 1, you probably saw these, or if you took Algebra 1, you saw them there. We got a couple of bubbles. The first bubble is for your inputs, and the second bubble is for your outputs. A lot of times when people see these mapping diagrams, they get a little bit confused about them because it doesn't look right for everything to be going to the same thing. But sometimes that can happen. You can have every single value in a function that's an input go to the same output. That's okay. If you think about the graph of that, it'd be a horizontal line. So just a flat line because everything has the same y value. One thing that a student told me a few years ago, they told me about airplanes. Has anybody heard the airplane analogy? No? Has anybody ever taken an airplane somewhere? All right. When you get on an airplane and you talk to the person beside you, are they going to a different place than you? They're all going, if you're going to San Francisco, they're also going to San Francisco because they're on the same plane. So if you think of these right here as airplanes, 3 different airplanes can all go to San Francisco. But you can't have one airplane that's both going to San Francisco and Orlando. That doesn't happen. So you can't have one number here that's going to 2 numbers there. That's not allowed. But you could have 3 different numbers going to the same place. All right, so next and last representation is the graph. And when I did those cards a little while ago, most of you guys drew a graph for me. You showed me a graph and you told me that a function is something that passes a test. What test is that? The vertical line test. So a function is something that passes the vertical line test. So you can draw anything, and as long as you can draw a vertical line through that, it's going to be considered a function. All right? So next blank. The inverse of a function. That's what our lesson is really about today. The inverse of a function is a relation obtained by reversing inputs and outputs. Go ahead and turn that off for just now, please. Relation obtained by reversing the inputs and outputs. So everything we saw up there in that empty space, we're switching the order. So the x's become the y's, and the y's become the x's. Then we have a little notation before we put this definition to work. When you see that little -1, a lot of people think it's an exponent. But that's how mathematicians say that this is the inverse of the regular function. So we read it f inverse of x. It's just the inverse of the function f of x. All right, so looking ahead, in those first set of boxes, you have 4 boxes down there. The first thing it asks is the relation a function? So you've got a bunch of ordered pairs like we saw here. We've got to decide whether or not this is a set of ordered pairs that is a function. The best way to think about this, in my opinion, is to look at the x's. So I have a 2 and a 3 and a 4 and a 5. Did my x's repeat? No, they're all different values. So is this a function or not? Good. This is a function, so you can write yes there. If I had seen one repeat, I just have to check to see if it gave us the same thing when it repeated. As long as that happens, it should still be a function. Find its inverse. According to this right up here, the inverse is what we get when we reverse the inputs and outputs. So we switch the x's and the y's. So if I take this ordered pair, I'm going to reverse the order on it. So instead of 2, 4, it's going to be 4, 2. Instead of 3, 5, it's going to be 5, 3. Instead of 4, 6, it's going to be 6, 4. And by now, you are intelligent human beings, and you kind of get the drift. 5, 7 is now 7, 5. So this is what we're going to do on all 4 of these in the boxes. Yes, Victoria?
What are the brackets for again?
The brackets just say that these are all together. So they're not easy to draw. If you're being careful, it's kind of like a 2 on top of the letter S. But I just kind of draw squiggles. So the question, letter C, says is the inverse a function? So if you look at what we just wrote down, Will is saying yes. Why is that, Will? None of the what's repeat. Good. None of the x's repeat. So yes, the inverse is a function. So we can write yes for that blank as well. So that's what you're doing for these. You're switching your x's and your y's, and you're seeing if the x's repeat. I want you guys to take a few minutes to do just that in the rest of the 3 boxes. I'm going to walk around. So in this one that you can see right here, did you say that this was a function or not? Yes or no?
No. Wait, which one?
This one right here.
That's a no. Oh, yes.
The original one that I've underlined in yellow is a function because every input gets the same output. So when I put something in, I get something out. It's always going to be the same thing I get out. The x's don't repeat. This is a function. When you reverse the order and you put the 1 first and the -1 second and the 2 first and the -2 second, was the inverse a function? Yes. Because even when I reverse the order, my inputs will always go to the same output. What about in this one? 2, 4, 4, 8, and 8, 8. Is the original a function or not?
Yes.
Yes, it is. The original one is a function because 2, 4, and 8 are the inputs and they don't repeat. The inverse is not a function. Why not, Charles? Good. I have 2 8s. That will be my new inputs, so they repeat and they don't give me the same thing both times. In the last one, function or not a function? No, why not? Those -2s, all right? So we can't have that repeating and have different outputs for each of them. If I put in a -2, I should always get the same thing out. Is the inverse a function when I reverse the order?
No.
No, why not this time? The positive 2's this time, if you look, I have a 2 for the y here and a 2 for the y there. And when I reverse them, they'll be x's. Good job. All right, raise your hand if you got all those right. Awesome. Good job. Okay, so now we have another vocabulary word, filling in this blank. If a function has an inverse that is also a function, we call it 1, 2, 1. So if the original is a function and its inverse is a function, we call it 1 to 1. All right? So every x goes with one y, every y goes with one x. We have a 1 to 1 relationship. Would this one, the last one we did with that big star beside it, would that one be considered 1 to 1?
No.
No, because neither of them are functions. It can't be 1 to 1. Both have to be functions. What about this one with the green star? Function or 1 to 1 or not? It's not 1 to 1. The original was a function. The inverse is not. What about this one, the second one with a pink star? Yes, because the original is a function and the inverse is also a function. And you guys already know the answer. Is that 1 to 1? Yes, good job. All right, so it's only 1 to 1 if both of them are functions. Now let's look at the bottom of that first page and fill in this information. Find the graph of the inverse of a function. Slope is the number that the x is multiplied by. What number is this little x multiplied by? If there's no number written there, there's an understood 1. Good job. So I've got y equals 1x, so my slope is 1. Hard for me to write that. Slope is 1. What's the y-intercept? The y-intercept is supposed to be added or subtracted out here. I don't see anything added or subtracted, so what's the y-intercept? Instead of a 1, because I would see a 1 if it was written, a 0. I can add a 0 without changing anything. So my y-intercept is 0. And you can see that line already graphed over here on the graph we have. We have a y-intercept of 0, and it has a slope up 1 over 1, up 1 over 1, up 1 over 1, forever and ever. So that's the line that it's talking about, y equals x, right here. All right, so to graph this, we've already got a function graphed here. We need to come up with the values when we plug in a -3 for x. So if you come over here and you look at this parabola-shaped graph, what do you get for y when you use -3 for x? If I look above the -3, what do I see there? What value is that? Y value. 7. All right. We're going up 1, 2, 3, 4, 5, 6, 7. And that's where we're crossing the value. Now, my line makes it look a little bit confusing, but on your paper with your pencil, you should be able to see that. What about at 0? If I'm at 0 on the x-axis, what y value goes with that? 1. Good job, Damian. And if I go over to 3 on the x-axis, what y value is graphed above it? 7 again. All right, so right above 3, the graph doesn't show up until we get to 7. All right, so we've got our regular function. We know some values in it. To get our inverse, we're going to take all of these y's and put them in our new x column. So 7, 1, and 7. And we're going to take all of these x's and we're going to put them in the new y column. So -3, 0, and +3. And then we're going to graph those. So I graph 7, -3, 1, 0, and 7, 3. So let's see who remembers how to graph points. Once you've got your 3 points graphed, draw in a little sideways parabola. catch up with us here. All right, you need to write down this one. Okay. And then we're going to graph. Yes.
So I'm not sure if I know this correctly, but like technically, shouldn't I just be able to count how many spaces there are in the line?
Yeah.
So for this one, isn't it like one space this way?
Yeah, the graph
Is
is
it
kind of
just
weird
on
looking. Yeah.
Okay.
Because if you look at them, these aren't really little squares, they're little rectangles.
Oh, yeah.
So it's not working out the way we think it should. Okay, so looking around at papers, a lot of us have graphs on here. Okay, then write something down so I stop thinking you're asleep. Okay, so the question that we need to answer, once we've plotted the points for the inverse, do you think that this function, the original one that we had, the one that was on our paper when it was copied, do you think that that was a one-to-one function? Was the original and its inverse both a function? No, we could see that this was a function to begin with, but this one, what gave away that it was not a function? There's two things that you should see. The sevens repeat, and we don't get the same thing out when we put the 7 in each time. And what about on the graph do you see that makes it not a function? You all remember that test we talked about? Doesn't pass the vertical line test. Vertical line test fail. So this is not a one-to-one function because the inverse is not a function even though the original one is. Now, in that next line, using the graph of the function, you can determine if it is one-to-one. So even without graphing this, even if this little guy wasn't here, if it had never happened, there is a combo test we can use. It's the old faithful vertical line test, but also its buddy, who you may have never heard of before, the horizontal line test. Because if it passes both of those, it's going to be one-to-one. If it passes one and fails the other, it is not going to be one-to-one. Who thinks they know what I mean by horizontal line test? I didn't really tell you what that meant. Damian, say it loud.
We'll take a line
Yeah.
sideways and then just...
Take a line sideways and see if it crosses more than 1 point. In this case, a horizontal line does cross more than 1 point, so we know even without graphing that other little sideways parabola that this is not a one-to-one function. Victoria also asked a good question a little while ago that I don't think everybody heard, but she remembers from probably Math 2. She remembers from Math 2 that because this is a reflection over this line, you can just kind of count how far it is away from the line above it and move it the same number of points away on the other side. And that can be kind of confusing sometimes, especially when you have a graph that's as messed up as this one. So I like using the tables, but that is still something that works. Good memory. All right, so now we only have to do one more thing, and that is find the inverse algebraically. So flip your paper over, because we're on the next side. Flip. Good. Good. And we're filling in number 1 at the top. You guys already know this step, probably. Well, maybe not. Whoops, sorry. Too far. One thing we're going to do just to make our lives a little bit easier, even though you don't have to if you feel like you're okay without it, I like to replace the f of x with a y. Just because writing f of x over and over again is not usually fun to do. And f of x is the name for the output, just like y is the name for the output. Keep your eyes open. All right, so replace f of x with y. Your second step, switch the x and the y. Remember, we switched the x's and the y's in our tables so that we could switch them in our graphs. We switched them in our ordered pairs. We switch them now. So inverses always have this step, switching the x's and the y's. And next, we solve for y. We get y alone. Yep.
When I switch the x and the y, is the 3 going to come with the x?
No. So just the letters move, not the numbers around them. Good question. The last thing we do, there's not really a blank for it because sometimes we don't necessarily care too much about it. Sometimes it's not necessary. Once you've gotten y alone, we put that f of x back in there. But this time we use the notation with the little -1 because it's not f of x anymore, it's f inverse of x. We found the inverse. So let's do that with this problem that we have in this blank space at the top, the 3x plus 2 there. First thing we're going to do is we're going to trade out the f of x with a y. So find your f of x, here it is. It's no longer an f of x, now it is a y. So we have y equals 3x plus 2. All right, so trade out the f of x with a y, switch the x and the y, and then we need to solve for y. Solving for y in this problem has 2 steps. Thank you. The first thing we need to do is subtract 2 from both sides. So I'm going to take this -2 here, -2 there, because I'm trying to get y all by itself. So I'm going to subtract. X minus 2 is not -1. It's not -2x. They're not like terms, so you have to write x minus 2. Meanwhile, over here, 2 minus 2 is 0, and all I have left is 3 times y. How do I get y alone now that I've done that first step? Colin? Divide. So both sides get divided by 3, and y is all by itself, because 3 divided by 3 is just a 1. 1 times y is just a y. So I end up with y equals x minus 2 divided by 3. Now some people like to keep going, and they like to say that this is y equals x divided by 3 minus 2 divided by 3. I don't need you to do that. You can stop right here if you want to. But that last thing in green there says replace the y with an f inverse of x. So I am going to take out this y and replace it with f inverse of x. So I know it's not the same thing as what we started with. Now a few of you all have already started working ahead, which I love. Some of these problems that you'll see won't have an f of x in them, especially on your homework. They only have y's. If it's a y to begin with, it needs to be a y at the end, and all you're going to do is put a little -1 up there beside the y. So this right here is the same thing as this right here. It just depends on what you started with. In this case, I started with an f of x, so I want to finish with an f of x. We just throw a little -1 up there. Because technically, if you write f inverse of x, we're saying that this is the inverse of f of x. And f of x is what we started with, and so we want to finish with its inverse. If you started with up here just a y instead of an f of x, we want to finish with the inverse of y. So we'd finish with y inverse. So it's just a notation thing. It's not the end of the world. It's not the most important thing that we're doing today, but it is something that you'll see on multiple choice tests. Bailey?
So if I start with a y, and then it needs to be a y to be negative.
Yes.
But if I start with an f of x, it needs to be the f minus 1.
Exactly. If you start with a y, you need to end with a y inverse. If you start with an f of x, you need to end with an f of x or an f inverse of x. If you start with a g of x, you need to end with a g inverse of x. If you start with an h of x, you need to end with a h inverse of x. So it's kind of, once you start, you get the hang of it. All right. So there's a bunch of problems down here. And the first two, you guys just saw me do some just like these. So we need to finish up the rest of these squares by following those steps at the top, the 3 steps, 1, 2, 3. I want you guys to try those first 2 that I just put blue boxes around right now, just to see if you can get them. Walking around the room, I've checked some people's papers. This one you should have an x plus 1 divided by 3. And in the next one, you should have f inverse of x equals x plus 5 divided by 2. Any questions on those 2? Will?
Can we just leave it as y?
Well, on this one, it started with an f of x, so we need to end with an f inverse of x.
Oh my.
All right. Okay, so I've gotten a couple questions about that. Whatever we start with, you want to end with the inverse of that. We change it to y so that we can work with it a little bit more simply. But if you started with something and you traded it out, you got to trade it back out. So make sure that you're doing that on both ends. Okay, so over here, some of you all have started doing this one, but there's something really important that a lot of people forget on problems like this. What do I do first? Before I even switch anything, I'm going to change this to a y, and then I'm going to switch the x and the y. And y'all have already figured out you can probably do that all in one step, because it's not a hard step to do. Okay, so after that, what is the opposite of squaring something so that I can get the y alone? Square rooting. So we know how to do that step, but a lot of people forget that you can't just write the square root of x here. Whenever I'm solving an equation and it requires me to take a square root of both sides, there's a little symbol that I have to put out in front of the square root. Have to put, not an I this time because there's no negative, plus or minus. Whenever I take a square root when I'm solving an equation, I have to put a plus or a minus. And that's something we like to leave off sometimes. I'm going to trade out my y with an f inverse of x. And I got my answer right here. Okay. Any questions on that top row? All right. Next one over. Ooh, I already did all those. That doesn't seem fair. To the first row. What you got left?
Okay.
You good? Just change it out. Okay. On the next slide, we're going to do the next row. And you guys are going to see some of the work that I've already done. This is the work that I also did in the video that was on Blackboard already last night. I used pretty colors. The first thing we did in pink on all of them was we traded out the f of x for a y. So that's the first thing I did in pink on all of them. After I did the pink step, in the orange step I switched my x's and my y's. And then after I switched my x's and my y's, in my yellow step I started solving. One thing that I mentioned in the video is if you do something that's affecting the entire side of an equation, you've got to undo that first. So in the middle one right here, I had a square root that was affecting the entire side of the equation. I can't do anything to take that 3 out of it until I get rid of the square root. Same thing here. I had a divided by 2 that was affecting the entire side of the equation. I can't do anything about that plus 7 until I get rid of the divided by 2 that I have. So, to undo division by 2, the opposite of dividing is to multiply both sides by 2. So, I want you guys to try these 4 problems. If you need to look up here, but know that copying something does not mean that you understand it. Try to do it without looking and then see if you're doing it the right way. Yes?
I did this before you put that out there, but why wouldn't the y be under there still?
Okay. One good question was, people were a little bit confused about how I wrote this one over here where I'm drawing the blue arrow because it looked like I was squaring both sides. What was I meaning to show you in that step? Multiplying by 2, because the whole side was divided by 2. So I'm trying to show you that I'm multiplying by 2. Thanks. Thanks for taking the hat off. All right. In the rest of them, if I put numbers on them, I'll call this one 1 and 2. Does anybody have any questions about how to do either of those? 1 or 2 where I put those numbers just now? Okay, Victoria?
For number 3, or number 2,
Uh-huh.
you have to
on that side?
Oh, good question. We are going to do a square root, but not first. The first step we'll do after we switch our x's and our y's. Does anybody know what we should do first?
-3.
-3. So we got to do the -3 before we take the square root. So we're not going to take the square root until the only thing on this side is the squared. And then we'll take the square root to undo the squared. But when we take the square root, what can we not forget? Plus or minus. And then, yes, the parentheses will be gone. And I'll have a y minus 1 equals plus or minus the square root of x minus 3. But now I have to get rid of that minus 1. What's the opposite of minus 1? Plus 1. So I'm going to add 1 here, and I'm going to add 1 over here as well. Sometimes people think that when I add 1 to the left-hand side, I'm going to get a -2, because -3 plus 1 is -2. But the -3 is inside and the plus 1 is outside. We can't let those two mix. So you have a couple options for how you can write that. You can do plus or minus the square root of x minus 3 and then put the plus 1 over here. Or you can put the plus 1 at the front and put the square root of x minus 3 after it. So you can write it either of those two ways. But for either of those two ways, I'm going to need to erase a little bit. Either of those two ways, we're going to have to put equals f inverse of x. All right. So either of those work, but that's all for number 2. I just couldn't fit it all. Colin? For you guys to do in groups, on this activity you'll be doing stuff like this. If you need to finish those 2 last problems on your notes, you can do that first with your group, and then I can help you if you need to. So I'm going to pass out the activity.